What happens to race car drivers when they eat too much? They get indigestion. Indigestion. How about that, folks? This is just some geometry that's involved when you have a linear system with two variables. You know, there are really just three things that can happen in terms of the solutions. So in each one of these diagrams, I have one line that's already plotted, and we're going to plot a second line in each one of these. And case 1, case 2, and case 3, we're going to draw our second line a little differently just to examine the variety of scenarios that arise when you have two lines plotted together in the coordinate plane. So here we have the line, looks like it has a negative slope. One thing that can happen is that there can be a second line that maybe goes like this, in which case it would appear as though the two lines intersect each other. So one way of describing what we're seeing is to say that the lines are intersecting. Now for a line that's intersecting with another line, you probably know that their point of intersection is pretty important, right? Point of intersection appears to be somewhere right here, and that point of intersection actually serves as the solution to the linear system that corresponds to these two lines. But it looks like they're only intersecting in one spot, which is actually the case here. So in terms of number of solutions, there's something to be said about that. How many solutions would there be to something like this? One solution, yep. So a system like this does have some terminology involved with it as well. It's called a consistent dependent system, which I'll add right here. You could also have two lines that appear to not intersect at all, in which case that would be the situation where the lines are parallel. If two lines are parallel and they're not intersecting each other, are there any solutions?
No.
Right. So this would be a situation where the number of solutions is 0. And anytime we have a system where we have parallel lines that aren't intersecting and the number of solutions is 0, we can consider that system as an inconsistent system. What's one more thing that can happen if we have a line plotted with another one? Yeah, infinitely many solutions or one line on top of the other. You're exactly right. Yep. Another thing that can happen is our second line coincides with our first line, in which case any point that's on the first line is also going to be a point on the second line. And so, technically, any point on the first or second line would serve as a solution to the system. So all of the points on these two lines would serve as solutions. And since lines are indefinite in the sense that they extend in both directions forever and ever, this would indicate that there are infinitely many solutions. So I'll indicate that with the infinity sign, a little hyphen there, and the word many. So infinitely many solutions. And I like to describe a system such as this, or what the lines are doing, as overlapping, or one line is on top of the other. I liked what Ross put in the chat bar there. And there's a special name for a system such as this. It's called, this is actually consistent dependent. I'm noticing I may have forgotten something with the case 1 scenario. This is consistent, my apologies for this, by the way, consistent independent. Sorry about that. So just make sure you add IN to your dependent word of case 1. Case 3 is a situation where it's consistent dependent. And the major deal there is it's dependent in the sense that, the solution coming from one line depends on the solution from another line, since they're overlapping each other. Okay. Any questions so far? All right. So as you add more and more of these variables into a linear equation, there's some modification of geometry that happens. So for example, when we plot an equation with two unknowns, we usually do that in the coordinate plane, which is two-dimensional. All right, that's a two-dimensional apparatus. When we have something that, when we have a linear equation with three variables, um, that would usually be an entity that lives in three-dimensional space. Um, and what it produces when we have an equation in three variables is a plane. And we can add a fourth variable, in which case, we work in 4 dimensions, and we can continue on until we work in what's called n-dimensional space, which is something that we'll be doing quite often in this class. Even though we can't visualize things that are in 4 dimensions or higher, we can still do some algebra in those dimensions, which I think is kind of a cool thing. So anyway, the graph of the equation ax plus by equals c produces a line in 2D. Now I want to give you some notation for two-dimensional space. We would usually write that as capital R with a superscript of 2. And we say this notation as 2 space. Now adding a third term with our third variable on the left-hand side of the standard form equation, as I mentioned, that's going to produce a plane, and that plane is going to live in three-dimensional space, which there's a notation for that as well. It's capital R with a superscript 3, and we would read that as 3 space. In the most generic sense, we could have an equation with n variables, right? So I'm going to write our linear equation in n variables. An equation such as this produces what's called a hyperplane. And I'm going to say that that's produced or lives in the, I'm not going to write ND, I'm just going to write this as R with a superscript N. And we would refer to that notation as N space. Does anybody know what we would refer to, or what we would read this as? That would be MySpace. Anybody remember that social media platform? MySpace? Yeah, it definitely got beat out by Facebook once that came on the scene. But yep, I'm sure my MySpace account is probably floating around out there still somewhere. Nothing interesting though. So, yep, that's just kind of me joking around. But anybody have any questions about what we just went over for that? So I want to take a look at the case where we have multiple planes plotted in the same three-dimensional coordinate system, and regardless of us increasing the dimension and changing the geometry of what our equations produce, we would still be concerned about the number of solutions to the system that corresponds to these entities. So we're now going to examine visually the number of solutions to linear systems that have 3 unknowns. All right, and solutions in a scenario such as this are really identified the same way as they were with the 2-line situation, where we want to find any points of intersection between the 3 planes. All right, now if it's going to be a solution, remember, a solution has to satisfy all the equations involved in the system. So if there's a solution to the system, it should correspond to a point that's on all 3 of the planes at the same time. Okay, if we find that there's a point that's on two planes but not on another plane, then that's not going to be a solution to the system. All right, solutions have to satisfy all the equations, and from a geometry standpoint, the solutions will be points that are on all of the planes at the same time. All right, so we're going to work on the first row here, and we'll try to identify where the solution or solutions are, and then we'll just make a note of how many solutions there would be to that system. So I want to make a note before we do that. Note right here, there are 3 planes in each diagram. All right, and the reason why I mention that is some of these diagrams look like there might be only 1 plane or 2 planes, but we're to assume that there are 3 planes in each diagram. Okay? So starting with the first box of the top row, we've got 3 planes. We've got this one right here. We've got one kind of coming out of the page. And then we've got this one right here. And do you think there's a point of intersection?
Yes.
Yep, definitely a point of intersection here, and maybe you might be spotting that point as being right here. Confirmation on that?
Mm-hmm.
Yep, that right there would represent a solution to the linear system with 3 equations and 3 unknowns. And that's actually the only solution. That's the only point where all 3 planes coincide with each other. And you can kind of think of this as, like the corner of your room, the floor and the 2 walls that meet up with each other. There is one point that is in connection with, all 3 of those planes, the floor and the 2 walls, and that would be the very corner of your room, right? Which, by the way, it is winter, so if you are cold, I always recommend standing in the corner of the bedroom because it's always 90 degrees there. No? All right, so the number of solutions to this system is just 1. Okay, so just that corner point. With our second diagram, we're seeing 3 planes again. Here's a plane. There's a plane. And we've got this as a plane. Are these planes intersecting each other? If so, in how many spots? Yeah, actually, there's more than just one solution to the system. If you take a peek right here, okay, that line that is formed when you intersect these planes in this way serves as solutions to the system. Now keep in mind, these planes extend, indefinitely, in their respective directions. And what ends up happening is, we can describe this solution in a geometric way. The solution would actually be a line. All right, and a line has infinitely many points on it, so the number of solutions to a system like this would be infinitely many. Okay, so in one case we have just one solution, and the geometry of that solution is a point. In another case, we've got infinitely many solutions, and the geometry of that solution is a line. Now, what's happening in the third diagram is all 3 planes are on top of each other. Okay, so any point that's in one plane is going to be a point in the other 2 planes, and so on and so forth. And so, this is another situation where we have infinitely many solutions because planes are infinite in the sense that they extend, in their 2 directions. And so infinitely many solutions for something like this as well. But the geometry is different in this scenario, okay? We had a point, a line, but the geometry of our solutions for the third scenario is actually a plane. All right, so that's going to be something that we address from time to time, is not only the number of solutions, but can we describe the geometry of this linear system just by virtue of the solutions to it and their format. Now, I mentioned that all diagrams have three planes in it, and this last one looks like there's just two, right? But what we're to assume with this last diagram is that two of these planes are intersecting each other, so or on top of each other, I should say. So let's maybe assume that this plane right here is on top of a plane in the same position, and then here's our third plane. Can anybody describe the geometry of the solutions to something like this? So all three planes are intersecting each other, and yep, they intersect each other in a line. So all of these are points of intersection, and they would trace out a line, yielding another system that has infinitely many solutions. So let's look at some other scenarios. We'll work on the bottom row now. Here we have three planes, and just by virtue of the way these things are drawn, it appears as though all three planes are parallel to each other. And I'll let you know that that's something that we can assume in this diagram. So all three planes are parallel to each other, but they're also all separated from each other. So do you think there's ever going to be a point that lies on all three planes at the same time?
No.
No. So the number of solutions to something like this is simply 0. Now another diagram where it looks like there are less than three planes, but kind of like the very last box of the top row, let's assume that we have two planes overlapping each other. So let's say that this is one plane that's overlapping with this plane, and then we've got the parallel plane that doesn't intersect those other two. So in terms of solutions to a linear system with three unknowns, okay, a solution doesn't change. The definition of a solution doesn't change its meaning. So if there were a solution here, it would have to be a point that's on all three of these planes at the same time. Now, granted, there are infinitely many points that are on the blue and green plane at the same time, but none of those points would actually also be on the orange plane. So in terms of a solution, there's not going to be a point that's on all three of the planes at the same time. So this is another no solutions situation. Do you think there are going to be any points that are on all three planes at the same time with our next diagram? No. Now, if we were just considering two planes, okay, then we could see that there are, infinitely many solutions with a situation like that. But with three planes here, a solution should be a point that's on all three at the same time, and there's not going to be a point that satisfies that. And it wouldn't take too much of a stretch of the imagination to find that there are no solutions to our very last diagram as well. So let's make a connection between the lines cases and also these recently developed plane cases. With regard to what happens in terms of the number of solutions in the two-dimensional situation, we saw a system having one solution, we saw a system having no solution, and we saw a system having infinitely many. Now, if we look at the conclusions for the intersecting planes, or lack thereof, we do see that a system can have one solution. We also see that a system can have infinitely many, and we also see that a system could have no solution. And before I make the jump to the overarching concept here, so a solution to a system such as this would have to be a point that's on all three planes at the same time. Now, if we just consider two planes at the same time, maybe the green and the orange one, then these would represent solutions. But that would be only if we had two equations with the three unknowns. Another scenario might be if you have the blue and the orange plane, only those two planes plotted together, in which case, you would have infinitely many solutions to a system like that. But do keep in mind that we're to assume a linear system with three equations and three unknowns. So there's actually no point that is on all three planes at the same time. All right, these pink lines that I had drawn would be kind of like special cases where there's just two equations with the three unknowns. But assuming three equations with the three unknowns, there's not going to be one point that's on all three planes at the same time. So you might have a point that's on two planes at the same time, but whatever two planes that point is in common with, it's not going to be in common with the third plane. So because there's no possibility for a point to be on all three planes at the same time, there's actually going to be no solutions to a system like this. So a solution has to satisfy all three equations at the same time, and you might have a solution satisfying two equations, but it wouldn't satisfy the third. So this is where we'll end things for today. Very important concept that does come to bail us out every now and then throughout the course. So regardless of the number of equations and unknowns, right, there are only three things that can happen with regard to the number of solutions, okay? A system may have one solution. A system may have no solution. Or a system may have infinitely many solutions. Of course, I was writing that as infinity sign dash many. But what's pretty striking about this is that there are no other possibilities. So let's look at what it's not saying, okay? This is not saying that a solution can have two solutions and only those two solutions. That's not possible, okay? If you find that a system has two solutions, I got news for you. There's actually infinitely many solutions to that system, okay? And this is not saying that a system can have only 100 solutions, okay? Because if you have 100 solutions to a system, there are infinitely many to it. All right. So when it comes to systems, no matter how chaotic and humongous they might look, you can always bank on there being 1, 0, or infinitely many solutions to that system. And there are no other possibilities.
Come on now, dog. Come on, man.